Good morning, sir.
Good morning.
I request Mr. Chandrakant to invite Dr. Ravinder Reddy, sir.
Thank you, madam. Good morning to one and all. It's a great pleasure for me to introduce our speaker, Dr. P.Ravinder Reddy, sir, who is going to deliver a keynote on mentionability and experimental methods. Dr. Ravinder Reddy, sir, has received his BTech from KITS Warangal, ME from PSG College, Coimbatore, and PhD from Usmania University. Ravinder Reddy, sir, has 32 years of teaching and research experience, and he is currently serving as Professor, Mechanical Engineering Department, CBIT. Sir has served in various positions as Principal, Head of the Mechanical Engineering Department, and Dean R&D. Sir has over 315 publications, international journals, and conferences proceedings, and has published 6 patents. 32 scholars have completed their PhD under his guidance, and 21 scholars are currently pursuing their PhD work under him. Dr. Ravinder Reddy, sir, has delivered 125 keynotes and invited talks. He has a chief and principal investigator for 26 research and 131 industrial consultancy projects sponsored by AICTC, UGC, DRDL, BHEL, etc. Ravinder Reddy, sir, has received 17 awards that includes Raja Ram Bapu National Award and Engineer of the Year Award for outstanding contribution in education and research. He is a member of several bodies like DRC BOS of Usmania University and JNTU Hyderabad. He is also a research member of DRDL Council. He is a life member of several professional societies. So I welcome Ravinder Reddy, sir, to deliver the keynote speech. Sir, we welcome you, sir.
Yeah, thank you. Good morning. So they introduced me twice, because yesterday and today. Good morning, all of you. Today, this session, I'll be speaking about some of the research which we have carried out on the metal matrix composites. You know, the machining of composites are very difficult, and estimation of the parameters for various applications. So machining is essential. The topic which I have selected for this session, machinability of metal matrix composites using numerical and experimental techniques. So all of you, those who are really working on machining of any alloys or composites, you know how the cutting parameters influence the machinability. And the same, suppose you wanted to simulate it. So in the simulations, we use implicit simulations and explicit simulations. I just wanted to present you, when you use the simulations, maybe a finite element analysis, implicit finite elements and explicit finite elements. When we model the cutting of any kind of process, whether it's orthogonal or oblique cutting, when we want to estimate the influence of the cutting speed, feed, depth of cut, you need to calculate energy. So in the finite element simulations, we need to apply thermomechanical analysis. When I say thermomechanical, we can apply for steady state conditions, transient conditions. So these are all the processes which I wanted to present you all. When we do the machining, experimentally, how the cutting parameters influence on machinability. Whenever we adopt numerical techniques, one of the important things in the numerical techniques, when you adopt, we need to see the material models. Whatever conventional the modeling is not suitable for manufacturing process. So in the manufacturing process, always we have to see the non-linearity of the materials that we are machining. So I just wanted to give you the flow process using implicit as well explicit finite element simulations in addition to the experimental work. As you all know that composite materials are classified into two types: metal-based composites like solid metals with materials such as silicon carbide, aluminum oxide, etc. Non-metal based composites, we know the polymer composites, ceramic matrix composites. Metal matrix composites form one group of new engineering materials that have received considerable research since the first trial by the Toyota in the early 1980s. MMCs are multi-phase materials consisting of ceramic reinforcing fibers, or you can reinforce viscous, or particles or particulates suspended in a metallic or intermetallic matrix. Metal matrix composites offer various advantages in applications where high specific strength, stiffness, and wear resistance are required. In a present case, the aluminum alloy reinforced with ceramic particles is the most popular type of MMC used in aeronautic and aerospace industries because of its lightweight and specific strength. Its importance not only because of higher strength, the stiffness, and fatigue resistance with a minimal increase in density over the base alloy, but also due to low cost. Most of the aluminum MMCs, through manufactured by different manufacturing processes, usually need machining operations for the required dimensional and geometric processing as well as for good surface finish. So all these characteristics we are going to discuss in the following presentations. The machining of composites differs from metal machining significantly in some respects. Unlike a monolithic material, composites have fibers or particles present in the matrix that are encountered by the tool intermittently. That means when the tool passing through, when you use the cutting process. So fiber matrix interface, then matrix. So this combination, because the tool is subjected to some kind of the dynamics. The mechanism of chip formation also differs with fiber angle in reference to cutting direction. Here also we will see some of the observations. Once the rake angle is changed, how the chip flows, how the chip is separated. During the separation, that intermittent, what is the temperature, what is the stress level, what is the deformation level. So all these characteristics we can see in simulations. Anyway, any experimental work you can see even naked eye those flow process. And if you want to measure the flow stresses and all, again we need to go for the simulations. Low thermal conductivity of a composite material causes heat buildup in the cutting zones, which may also lead to thermal degradation of the matrix. Due to enormous difference in the coefficient of thermal expansion between the particulates and the matrix, the residual stresses are generated. So here one observation you can make, because it's a composite, we have a particulates with a different thermal conductivity, and the fiber, the matrix, what you can use is a different thermal conductivity. So here residual stresses are differed in a location to location. So local finite element model, whenever you go for simulations, is essential because we have to assign the properties accordingly. The amount of heat generated is different from normal conventional material when you use for numerical or experimental operation. In addition to above problems, the chips formed on cutting of composites are very small and are literally in the form of a powder. This hazardous airborne dust may cause inconvenience while machining and can be removed by a dust extraction system. Hence, the study of machining of composites as a whole needs to be addressed separately with that of conventional materials. With this background, we are going ahead for our research work. This work focuses on metal matrix composites with a higher percentage of silicon carbide particulates. The explicit simulations are carried out using LS-DYNA on aluminum silicon particulates. The scope of the study In this work, experimental and numerical studies are performed on turning of aluminum silicon carbide composite. In turning using K20 carbide cutting tool, the experiments were conducted to measure the temperature along the cutting tool edge using thermocouples at various cutting speeds, depth of cuts, keeping the feed rate constant. So we have changed even out of three, one constant, other varied. Then finite element simulations were carried out. Wear patterns and the wear land growth rates are also analyzed using both experimental as well as numerical simulations and evaluate the wear characteristics and to classify the relationship between the properties. And we have evaluated the flank wear land growth on cutting tools. The flank wear rate was quantified by considering the tool geometry. Further, the modeling techniques on continuous chip formation by using the commercial FEM code ANSYS LS Dyna are also presented in the following slides. A combination of three chip formation analysis steps, including initial chip formation, chip growth, and steady state chip formation, is used to simulate the continuous chip formation process. When I mentioned this, when your chips are flowing, when they are contacting the work and then separating from the tool, it's going to be some kind of the fracture mechanics we have to include. Here, this fracture mechanics is again damage fracture mechanics with thermal degradation. So this is a coupling of a lot of our engineering disciplines. In this cutting process, steady state analysis as well transient also performed to predict the variables contact pressure, we evaluate the normal stress, a tool chip interface and tool work interface using relative sliding velocity and cutting temperature distribution. So when we use the chip flow or the tool movement while keeping the work constant, there are two ways we can use in the simulations. One is you can have a dynamic mesh. That means when the tool is moving towards the work and there is a chip is flowing, to simulate such, the mesh is not going to be stationary. The element earlier in contact will go away further and the next element should come in. So here the moving mesh concept is being adopted. It is shown that tool wear rate is dependent on these cutting process parameters and the relationship is described by wear rate models. Then the tool wear progress in turning operation is determined. The aluminum silicon carbide particulates MMC material with aluminum 6061 as a matrix with 10%, 20%, and 30% is the silicon carbide particulates of size 10 to 30 microns dispersed uniformly. So the influence of this silicon carbide particulate 10, 20, 30%. When this size, how it is influencing on the temperature distribution, thermal stresses, and thermal distortion. Dry cutting tests at different cutting speeds, feed rate, and depth of cuts were conducted in order to investigate the effect of various parameters on surface quality. So we have measured the surface finish with those parameters while varying. In addition, the surface roughness of the specimens is evaluated with respect to volume fraction of silicon carbide particulates. The cutting tests were conducted using K10, K20, P20, P30 carbide tools and polycrystalline diamond tools to evaluate their relative performance. So comparison of all these, either you can measure the tool wear and the temperature and the thermal stresses and distortion, and we can conclude which is going to be the best material for the cutting operation of this and what conditions the tool wear is less and what rake angle it is. Again, the continuous chips are formed or brittle chips are formed and how the chip separation process is taking place. This is an experimental setup in our lab, and we have a HMT, the machine, and we have the stabilizer and the bridge circuit which we designed for the temperature measurement of using thermocouples on the tools. and interfaces also you can measure. So this is the schematic outline and the bit circuit what we have designed for measurement of the temperatures. And we need to calibrate, so we have an oven and keep the same and change the temperature and measure the voltmeter. Then you will be knowing the scaling and you can convert based on the temperature which we obtain, and you can connect to this, then get the true temperatures that we can get on the tool. So because as when we do the experiments, one observation that you can make it, because if there is going to be rubbing, there is going to be the interaction between the chip tool work. When you measure the thermocouples, because these are contact type, so we can have 3 or 4 thermocouples located in different places. So 1 or 2 when break, the other will have the temperature, so that we can take the average temperatures wherever we are measuring, because this is not a non-contact type, so it's a contact type. Okay, when we use finite element, I wanted to give some introduction about the analysis that we perform. We do the linear elastic analysis where the material is elastic and geometry also is linear. So we can have the general steady state when we do the cutting operations. The linear elastic analysis is enough to get the thermal stresses because we are coupling the after temperature analysis, the change in temperature delta T will be knowing, then thermal expansion we know. So this will be automatically is initial strain. With the initial strains, when you do thermoelastic analysis, then we can get the thermal and residual stresses. And the other is the nonlinear material, nonlinear geometry also. So nonlinear material, because we are saying chip is flowing. If it is a brittle, linear is enough. When the chips are in contact, then there's going to be deformation while machining. Then we need to have the nonlinear material models. So here, generally, the D is the material matrix. So this D, no more constant. It depends on either deformation or the temperature. The stress by differentiating strain energy density, you can use the linear material, you can use the nonlinear material. Then stress is a function of strain, the deformation dependent in case of nonlinear geometry. And you can model potential and path independent analysis. Typically, when you see the relationship stress versus strain, there is going to be a material matrix. This could be linear, this could be nonlinear. So if it is a nonlinear, there is a functional which we are going to use, then the material model and geometric model is going to be a nonlinear. In general, if you want a stress in terms of energy, du by d epsilon, and energy, you can write off of E epsilon square, when you have a relation between stress and strain with Young's modulus. The linear nonlinearity, to understand better, if you take a spring model, the spring which elastic E subjected to a load, when it is increase the load, there is going to be straining. And if you plot this stress strain curve, if this behavior is straight, it's going to be, we call it's a linear, but the behavior is a curve, then you would see here there are the different slopes, whereas the linear constant slope. So we have models in metal cutting, viscoelastic materials, could be time dependent behavior. Sometimes we have to model creep and relaxation models also. The metal nonlinearity in case of elastoplastic material. So when you take such a system loading, when you load it, then I unload it. So we have this elastoplastic kind of things where you are after yield point, there is going to be unloading, and either at yield or after certain point, we can do it. So this history is required for material behavior whenever we model for manufacturing techniques. The viscoelastic material time behavior or K relaxation. If you see here strain rate, you can have the time strain or a material modulus or a stress. we can measure with respect to time in this relaxation techniques and creep. We have some contact mechanics because here chip and tool and work, there is a contact. So what contact analysis generally we do, the same contact we can also mention, we can also include in our metal cutting process. So here when you use the contact, there is going to be, contact is always non-linear, and you have the displacement, load dependent displacements, and we sometimes model kinematic nonlinearity. So when you see this roller and subjected to a bar and it is undergoing, so you have a deformation, you can see the plastic deformation. And this is the contact mechanics and the plastic deformation. So you can plot the variation of the load versus displacement. You have typically have this kind of behavior. And you have a bar subjected to a continuous loading, and again kinematic nonlinearity. So we have some cases, mild nonlinear problems, may be continuous, still independent, nonlinear relations between the stress and strain. The nonlinear elasticity, geometric nonlinearity, and deformation dependent loads, all these are factors which we need to consider. And you have a mild to rough nonlinear problems, equality or inequality constraints in constitutive relationships. History dependent nonlinear relations between stress and strain should be included. Elastoplasticity and contact problems will come under this. And when you use a simple linear problem, K is the stiffness. Stiffness, as you know, depends on geometry and material. And D is the displacement, and there is a force. When you use in metal cutting operations, first we do the heat transfer analysis. So K is the characteristic matrix, T is the temperature, then thermal loads, heat flux, heat generation. So we measure the temperature change. After measuring the temperature change, then you can use the material property, thermal expansion or contraction. Then we couple these temperatures to the structural. When it comes to structural, we can do the linear analysis, nonlinear analysis. If you use the linear analysis, the stiffness into the displacement is equal to thermal loads in addition to the cutting forces. Cutting forces, static forces. Because of contact, temperature induced, there is a change in temperature. You have a thermal load also. So here, this resultant load is load due to temperature change and in addition to that cutting forces, both together. So we can get the deformation, then strain stresses. These are the thermal stresses. And you can use nonlinear analysis, where when you use nonlinear analysis, the load and the stress depends on displacement. So these kind of solutions required either use incremental method or the familiar approach like Newton-Raphson method, modified Newton-Raphson method. Those approaches we use. So in nonlinear cases, equilibrium between internal and external forces, kinetic and kinematic nonlinears are included, appears on the boundary, handled by displacements and forces, either use the global static or steady state implicit, or you can go for explicit. Relatively easy to understand, not easy to implement though. Material, geometric nonlinearities appears in the domain, depends on stresses and strains. These are local and implicit analysis. Typically, if you see the geometric nonlinearity, typically a rod, when it's subjected to a moment, it takes this kind of large deformations, large strains. So those are all called the geometric nonlinearity. So if you can see the tip displacement versus the applied load, you have typically a curve. If you see the incrementally, then you can have a load increment, but basically load is constant. So what in the simulations or in the periodic of experiments when you conduct, we typically, the actual load, instead of applying the actual load, you increment it, then go to the final load. So then you get actual displacements. So mathematically you can say linear, simply epsilon x, then one dimensional typically, du by dx. But if you think non-linear, the error terms are removed here. So you can include the error terms. So these error terms will make there is a deformation large. The displacement strain relationship, you can see when you apply strain versus du by dx, how much deviation that you can see. And this E, when you wanted to calculate, then the Young's modulus, what actually you can predict or you can estimate. So you know epsilon x is du by dx, that is going to be strain actually reaching when the actual slope is going to be constant. When you calculate the energy or the stiffness for the member, then you can take volume integral or surface integral depending on our line integral. Depending on geometry that you are considering, then the other domain, then strain and stress, and for the same domain. So you have a strain transpose and sigma. Here non-linear because this stress and strain are depends on geometry or displacement. When you analyze, that's a structural part of it. Then you have a thermal part because our material getting constitute both thermostructural. So we need to do the heat transfer analysis. Sometimes we satisfy steady state heat transfer, but in reality we have to go for transient heat transfer. Now both the cases, you can have a linear analysis, non-linear analysis. What is linear steady state heat transfer analysis? Your material properties independent of the temperature. What is the material property required steady state condition? Only thermal conductivity. So thermal conductivity is the independent of temperature. And you have non-linear, means you are thermal varying with respect to temperature. So non-linear material. So then we have a transient heat transfer. In the case of transient heat transfer, linear. So here the material is linear. So in the case of transient, the material properties required are thermal conductivity, density, specific heat, or enthalpy, because there is a phase change. So that's why enthalpy or specific heat are required. So in linear analysis, your thermal conductivity and enthalpy are a specific heat and density are independent of the temperature. Whereas in nonlinear, those varies with respect to temperature. So when you want to have cryogenic conditions, you are cutting operations, we'll do a different temperatures. There the material might lose its property, and accordingly we need to have the real simulations. Typically, if you use the steady state heat transfer analysis. Hello? Anything? Okay. So when you use the steady state heat transfer analysis, typically if I take some volume and temperature anywhere, let us say T, X, Y, Z is your geometry, and small q is the heat flux, capital Q is the heat generation, and H is the convection. So in our thermal cutting, when you do the operation, H is going to be, when you use the fluid, right? So we use the fluid, so you need to use H. And contact, you can calculate heat generation or heat flux. Suppose if these are the conditions acting in our cutting process, we have the energy equation, the 3D conduction equation. So Kx, Ky, Kz thermal conductivities, T is the temperature, X, Y, Z your geometry. So we can write the energy equation as Kx dou square T by dou X square plus Ky dou square T by dou Y square plus Kz dou square T by dou Z square plus or minus Q equal to 0, heat input. This is going to be your geometry. If it is a 3-dimensional, all the 3 terms. If it is a 2-dimensional, first 2 terms, 1-dimensional first term alone. If there is a coolant, then we have to use the convection. In the same equation, we are using convection. The T infinity is the bulk temperature. The fluid coolant temperature, you can say fluid temperature or coolant temperature. So here heat generation, heat flux, heat generation is per volume. Heat flux is per area and convection is per area. Then you have a T temperature wherever you wanted to calculate. T infinity is the coolant temperature. So because steady state right hand side is 0, if it is unsteady state right hand side, you have a load dependent term will be there. And we need to solve this for the temperatures. So whenever you want to solve any the governing differential equation, we are going to use either two approaches, energy or weight approach. For doing such, we need to have a boundary conditions. The boundary conditions in any heat transfer analysis are specified temperature, maybe room temperature, etc. Heat loads, how much is the thermal load, heat flux, heat generation, insulation. So where it's the furthest, no contact, or there's a contact, then you can say heat flow is zero. Then sometimes we need to include radiation also. So here, this governing differential equation, the first part is heat due to conduction, geometry. And the second is heat due to generation, load. Heat due to heat flux. This is again load. And this is a convection load, heat due to convection. So we can use the variation principle or work principle. Then you can calculate total energy in the system. The energy in the system is the volume integral of your kx dou t by dou x whole square plus k by dou t by dou y whole square plus kj dou t by dou z whole square over volume minus volume integral q into temperature dV minus area, because q is area dependent, qt dA, and again h is surface dependent of area integral ht minus t square dA. So this is energy due to conduction, energy due to heat generation, energy due to heat flux, energy due to convection. All the summation of all these is going to be total energy. When you use a finite element analysis, you discretize the given body into small, small pieces. So what you have to do, this energy you have to calculate for the first element, then second element, then third element, and fourth element. And then total energy we need. So here, suppose you wanted to come to a certain concluding part of the terms related, instead of using all these variables. So here, the first one, the energy due to conduction, we say pi 1. The second is pi 2, third is pi 3, fourth is pi 4. The phi 1 alone, you wanted to simplify, which is the same thing written here. Then this we can write in a matrix form. So I'm writing here now the row matrix dou t by dou x, dou t by dou y, dou t by dou z, and the material matrix kx0, 0, k0, ky0, 0, 0, kz. Then again the column matrix of the temperature gradient. Now we designate this as the temperature gradient G. G is dou t by dou x, dou t by dou y, dou t by dou z. Temperature gradient x direction, temperature gradient along y direction, temperature gradient along z direction. And here this is going to be your thermal conductivity. If it is orthotropic, you have a thermal conductivity x direction, y direction, z direction different. Isotropic, it is going to be only one thermal conductivity. So D becomes K. And this we designate by capital D. Again, if this is going to be G and this is G transpose. Right? So now this same, if you multiply this into this and this into this, you will get the same. So whatever equation we have written in matrix form. Then this we can simplify half of volume integral G transpose dG. That's what we have written the gradient matrix dou t by dou x, dou t by dou y, dou t by dou z. Typically, if you take one element, maybe tetrahedron element, 4-noded tetrahedron element, the geometrically x, y, z, three-dimensional, and you have coordinates x1, y1, z1, x2, y2, z2, x3, y3, z3, x4, y4, z4. The temperatures T1, T2, T3, T4. As you know, we use the shape function. The shape function is, because you have 4 nodes, 4 shape functions, n1 to n4. Then T is the element temperature anywhere. So nodal temperature T1, T2, T3, T4. So as you know, that element temperature is equal to nodal temperature into the shape functions of nodes. So here temperature anywhere in the element is the shape functions of the element into nodal temperature. So nodal temperature, you can have the expansion N1 T1, N2 T2, N3 T3, N4 T4. It is separate. the shape function separated with the column matrix of temperature. NT bar, you can write. The gradient matrix, now dou t by dou x, dou t by dou y, dou t by dou z, dou t by dou x, we can write dou n1 dou x to dou n1 dou y. Dou t by dou y, dou n1 by dou y to dou n4 by dou y, t1 to t4. Similarly, dou t by dou z, this row into column. And here the gradient matrix is split into the B matrix, this is the temperature gradient matrix, into nodal temperature. So this matrix I've written here, this is going to be strain displacement like here temperature gradient matrix. Then material matrix, if it is isotropic, D becomes only thermal conductivity. Then we can write the simplification of this, the phi 1 is half of volume integral G transport dg dV. So the total energy, now we can substitute here, then loads, we can write the load, we can write, and the temperature is NT bar, right? You can write in terms of shape function and nodal temperature. Then you can write T transpose T bar temperature, the T bar into N here, T transpose is T bar transpose N transpose, N is missing here. G is BT bar, G transpose T bar transpose B transpose. Substitute in the above equation. And this results, this we can simplify. There's the total energy summation of those. Once you get the total energy, then differentiate the total energy with respect to nodal temperature, then equal to 0. That is your energy principle. So once you differentiate, then equal to 0, it results in this form. The first part is volume integral B transpose dB dV. The second part is area integral H N transpose N dA into temperature in the structure equal to then the load due to heat generation, load due to heat flux, load due to convection. When I convert this to metal cutting operation, this part is your geometry, tool, chip and work. This part is your coolant. Suppose no coolant, this is 0. And no coolant, this is 0 and this is 0. And here the heat contact, this is contact between the tool chip and work. These are the contact heat loads. And these two are coolant dependent. No coolant, these are 0. So that's what convection values. So this is the convection, the convection part of conduction. And this C1 plus C2, you can say C into T bar equal to load. So we can say it's going to be load. And these loads are, the first load is due to heat generation, second load is heat flux, third load is convection. That's what I mentioned here. Then you can combine these two, the characteristic matrix into nodal temperature equal to load matrix. So simply CT bar equal to F, solve for T bar, then you can get the G, then you can get all other gradient, because temperature gradient is required for us. This is going to cause thermal stresses, thermal strains. So we need to get this G value after getting nodal temperature. Then you can calculate the heat flow rate in our heat transfer analysis. Then we can see that once we couple to structural, then switch from thermal to structural, then we can get initial strains due to alpha and temperature change. So here the temperature change is this G. Alpha is a material property. So sigma equal to D into epsilon minus epsilon. Epsilon is the normal strain and epsilon naught is initial strain. This is your material property. So that causes thermal stress. So this is what we use in steady state solutions. But is it steady state enough for our metal cutting operations? Not. So we need to go for a transient. And we wanted to measure tool wear rate. Again, it is time dependent. We need to work transient analysis. The field problems considered earlier assumed to have reached the steady state condition before the analysis is undertaken. An equally important set of physical problems include those that are time dependent. The transient period for some of those problems occurs between the starting of the physical process and reaching the steady state condition. A steady state condition never reached in some problems, and the transient period includes the entire life of the process. The tandem problems are common and important in heat transfer. The quasi-harmonic equation contains time derivative term in a physical system. So this total, whatever you use steady state, the right hand side we have this the gamma of the and dou T by dou of T. So here dou T by dou of T is the time dependent temperature load. So this becomes the transient. And this is heat capacitance. Lambda is nothing but rho C, density into specific heat. So in our materials, the uh, density of the material and the specific heat of the material. So when you take work density and specific heat. When you go for the tool density and specific heat is going to be long. And your thermal conductivity is then heat energy. What is the difference in case of transient? Whatever right hand side is there, you take on the left side. The heat generation already is there. Because right hand side you are converting to left side. So this Q minus lambda dou T by dou T is the new term. This we can integrate and again use the same minimization process, and we can calculate heat loads from that, and we can couple. So whenever we use, these are all same as earlier. This K is C and phi is the, because why we modified phi, this is a transient one, and this is going to be load. This is a characteristic matrix. This is a temperature, time dependent temperature. So here the characteristic matrix into dou phi by dou T, time dependent temperature, we need to estimate. So for calculation of those, we have an additional term of capacitance matrix. So this capacitance matrix is volume integral. If it is 3-dimensional volume integral, 2-dimensional area integral, lambda into shape function transpose into shape function over volume. So lambda is rho C, and here this is the additional one in transient case, and that need to be included. Whenever you include time dependent one, we need to solve this either incremental step process, or you can go for any different scheme. So we use for the elements, the final equation we can write like this: C phi dot means the temperature dependent, time dependent temperature, and this is steady state. And this is the transient term of capacitance matrix. Capacitance, temperature, time dependent temperature is the additional term. Rest of the things same. So we can use forward, backward, central difference schemes to estimate by giving increments of the time, and you can calculate, because here additional boundary condition required is initial boundary conditions. Initial boundary condition nothing but at time t equals 0. What is the status? Solve first for that first iteration, then increment it. So we use both backwards, central difference, and or otherwise we can use forward difference method, Ehler's method, Crank-Nicholson scheme, Galerkin's method, backward difference method. So where we have given this equation in a generalized form, the theta values for those whenever we adapt, and that will be coupled. See, abacus or LS Diana, when you take all these models exist. Okay, with this background, we'll move on to the chip flowing process, real cutting process. This is conventionally when you see a small chips, this is a work, then the tool, then you have a chip. If you see here, the mesh density is going to vary, because here there is a shear zone. We need to have a more number of elements, and this side cutting, this is a contact between the tool and work. You should have more elements, and you have a contact between tool and chip, so you should have more elements. And for this we have removed, for this we have removed, and we are trying to have more number of elements, because this is a zone our important, and this zone is not at all bothered. Only for the sake we need to have some shape we have kept, but otherwise our total interest is only this part. So localized mesh, we need to have a grid size, the very refined mesh. And when you use the models already in LS-DANA, there are 64 material models you have. Even Abacus also similar. We can adapt some of the material models so that the coefficients will be available. These material properties we can assign, and the indices we need to specify. Typically, JC ordering method describes flow stress of material with the strain rate, temperature effect. So this is going to be the constants A, B, and you have a C, and ABC are given in the material strength values. So if you see sigma bar is equivalent stress, A is the initial yield strength for that material we know at room temperature. B is the hardening modulus. Epsilon is the equivalent plastic strain which we are going to measure. N is the work hardening component exponent. C is the coefficient dependent on the strain rate, and epsilon dot is the equivalent plastic strain rate. And again, we can have a reference strain rate. M is the thermal softening coefficient. And the room temperature and all we specify for the same. And the coefficients here again, when you go for the strain rate for fracture, when you have a damage mechanics is associated. We have the parameters like D1, D2, D3, D4, which we can have the constraints for these models available. And we can include these when you select that model, automatically these constants will be given. And we can calculate the deformation in terms of strain rate and fracture, the damage, because the chip, when it is separation, we are going to calculate the damage mechanics. So we use Hilbert's fracture energy. This is strain energy release rate. We will calculate for the slope of the same and the yield strength and the strain rate in plastic zone. So when we calculate the damage, the contact mechanics into the chip and tool contact, so automatically these we can select in our abacus model. Then the failures can be estimated. And the pattern of variation, so the progressive damage, especially for this is going to be a chip model. So what we are doing for the chip and work and chip and tool, only that portion we are going to have a localized fracture model. So fracture contact and all in, when you connect thermomechanical, the mechanical analysis, structural analysis, we need to include these terms. So elastic models, how it is increasing. We know the theoretical equation, the strain energy release rate with the stress intensity factors for plane strain and plane stress, the small variation we are going. So this is for the damage, and the other side, we need to define in our heat transfer analysis the heat flux. So we need to calculate heat flux between the tool and work, and heat flux between the tool and chip. So, and it is shear zone. So we have even any, this is one thing I have given here. Any metal cutting book, you will find all these, the heat flux along the tool work interface, chip tool interface, shear zone. Even those, whatever, those are mentioned here. And because when you go for a transient condition, this is a steady state condition. But when you go for a transient condition, that heat flux, the rate, because we need to model the chip rate and all, the specific heat we have to define and you can model. So according to the temperature change, the difference, what we can calculate. When you again link with this thermal variation in transient condition to the damage mechanics. So thermal and fracture, we have to couple and we can calculate. Generalized boundary conditions, but coupling all the flux have written a generalized way. Q of plastic is you have the mechanical coefficient and stress at the plastic equivalent the strain rate at the plastic rate, and heat rate per unit area and chip tool interface. So here fractional heat per unit area, you have a fractional coefficient, then you have a shear at that location, then you have strain slip rate. The material properties you can take, we can have steady state condition, the independent of the temperature, all the properties we can take, both aluminum, silicon carbide, then the tool materials, all the tool materials we can have the properties to assign, or you can select. Then experimentally with the bridge what we have defined when we operate at a different depth of cut and feed rate and varying the cutting forces, we can measure the temperature. So the temperature at different cutting speeds, because at the interface, midpoint of the interface. So we have given from the contact farthest away and you can have a average of these temperatures, tool temperature, tooltip temperature. So otherwise, the nearest and further away, we have calculated different speeds. So when you increase the speed, definitely you know that the temperature is increasing, and you can see the temperature variation between when the speed is 9.8 meter per minute, it's 165 degrees centigrade, and 50 meter per minute, it is increasing to 285. When you showcase the same in fundamental modeling, so here the damage mechanics, earlier I've shown is steady state heat transfer. When you want damage mechanics, we need to have a contact location for this and the very fine mesh. And when you have a tool, you can also see the tool. We have very high, because chip point tool is going to have a contact. That's why it meshes. And this tool is now moving so along the, if you say the radial direction, it is moving in the radial direction. And some of the analysis we performed with changing the rake angle. So when you change the rake angle again, remesh it, again you should have a contact, then you have to have the models. And we can measure the wear also, flank wear, right, and nose wear and all. So when such a model with different strain rates, we can calculate the full flow stress values at different temperatures. So when you plot flow stress versus effective strain at different temperatures, we can see at different strains, higher strains and lower strains when you observe, right? So this 10 to 5000, here at the lower, the higher temperatures, almost these are not affecting anything. But lower temperatures, if you see, there is going to be the variation among the strain rates. So that's the observations you can make it. When the chip is flowing, and you wanted to see the strain energy release rate, so energy, what we can calculate at different locations. When your chip is curling and even, so there is going to be a separation, break, connecting at certain points. And here you have a continuous form. So if you see the lower energy, it's breaking and discontinuous. And at the higher energy level, you have a continuity, so plastic deformation, and it is going to be very continuous. But high values at this place, high energy values. So you can see again for the rest increase in and 20,000 and 20,000. And you can also see the stresses induced. So almost it is highest at this level is around 70 megapascal. Similarly, this is going to be at different depth of cuts. So here, this depth of cut is 20 microns. Here, depth of cut at 20 microns and 50 microns. The energy is 12,500 per meter. And you can see at high depth of cuts, you have a chip separation, whereas their continuity is being observed. And here, again, with the constant energy and constant depth of cut, changing rake angles, zero rake angle, you have this pattern. 22 degrees, you have continuous, and again, there is a breaking, so somewhere. And you are at minus 30 degrees. You can see, again, it is coming back, and there's no continuity. And the minus value, so minus is not real simulation, what the real, how the actual work is in a progress in experimental. And again, here you can see chip fracture during serrated chip formation at different strains. So you can find out chip fracture taking place. There's going to be a connecting here. Okay, and you can see here because here you are getting rake angle 20 degrees is fine. Keeping 22 degrees, energy is 1500 is fine. So 1500, depth of cut 20 microns is fine. So, and we can calculate the plastic strain, how the plastic strain is going to be. So this is the real behavior, what is required. So this is the real behavior. We can fix it and we can proceed further. And when you compare the results, both experimental and the fundamental simulations, particularly temperature distribution. So we have plotted the temperature against the depth of cut. So this is experimental values. And we can see from the radial direction how the temperature is varying at different cutting speeds. And similarly axial direction. And also we can measure the chip thickness, so chip flowing process. The temperature chip tool contact is very high, and as one moves further away from the contact, there is a gradual decrease in the temperature. From these figures, one can observe that most of the heat concentration in the tool, this phenomenon is entirely different metals, where most of the heat is carried out by the chip. The reason for this behavior could be due to the difference in cutting mechanisms. In the composite materials, the cutting mechanism is more of brittle fracture, involving a combination of mechanisms like cutting, cracking, flowing, and abrasion. These are the four mechanisms observed in the cutting process. Very small contact length between the chip, dust or minute size of the chip, and the tool can also be explained as one of the reasons for the heat not being carried by the chips. And cutting temperature versus cutting speed, when you compare both experimental as well as numerical. So we have almost closed relationship, almost 1.5% variation here and there. Some places coinciding, some places deviating. After measuring the temperature, so then the stress strain rate and all, we need to estimate the wear. So you know the chip compression process and merchant tool, where the tool, how it is going to run. So the objective of this experimental work is to compare the results of the merchant equation with the experimental cutting model during the turning of mathematics composites with the PCD cutting tool. So here we conducted experimentation on aluminum composite with 70% aluminum and 30% silicon carbide with a diameter of 60 mm. The tool tips are square inserts 12.7 by 12.7 mm and 4.7 mm. SNP of 432 type with a tool geometry of 5 degrees, 5 degrees, minus 5 degrees plus, and 15 degrees and 0.8 mm, which are set in standard tool holder. The material of the tool tip is K20 carbide tool with a composition of 94% WC and 6% cobalt. So a depth of cut of 1 mm and feed rate of 0.1 mm per revolution remain constant through all the tests. Several spindle speeds are selected. Cutting fluid is used for washing of the chips. The flank wear lengths of tested tools were measured with Olympus STM tool makers microscope. The nose wear by Protosys subcam 2B submeter, and the work cutting edges obtained by Hitachi Akashi's MSM2 scanning electron microscope. The theoretical equation, what you have, cumulative damage of tool is summation T equal to 1 to K, because we are going to at the through contact the delta T1 dCt to the power 1 by n. In other words, Q C to the power 1 by n. So these are the material properties of the tools which we have used: carbide tipped K20, P20, M10, then ceramics, aluminum oxide with we have a titanium carbide. These properties are required, and you can plot nose wear and sectional area of the nose wear at different cutting speeds. So the cutting speed selected 14 RPM, 800 RPM, 2000 RPM, and you can observe that against number of cuts, when you increase the number of cuts, the nose wear is increasing. But increasing after a certain level, you can observe after this, it is again decreasing. Whereas the sectional area of nose wear is increasing. These dotted lines are sectional areas. So there is a constant slope, right? So this is linear. This is a small variation of these two, okay, at different speeds. But otherwise, you can say at a lower speed, right, and higher speed it's going to be very high. And nose wear land, you can observe at this location it is going to be very, very high, and that you can see the next slide that on the tool, the land wear on the edges, you can have a lot of cracks. And you can observe even more. This is a nose wear. And banded wear and carbide tool. So it is bonding like, so attachment. Okay, so there's no cracks and all. The compare wear rate on HS and K20 tool materials. These two are, you can have a comparison where you can find the deposition of. When you discuss these results, the wear progression, different volume fraction of silicon carbide. So volume fraction on the x-axis, you have a 10% and 20%. So then we have a measured one and a predicted one. So flank wear in mm, so you can observe the measured one. When volume fraction is increasing, it is increasing. In both measured and predicted. If you see here, we have progression at 10% dispersion of aluminum. So the measured is a black and white is predicted. You can observe here at volume fraction 9.5, 20, 25. Again, it is increasing. The level of increase and all, also you can see the magnitudes. We are the same flat wear rate, you can also see. Measuring at a different micron level. So we have 20, 25, again 20, 25, both measured and predicted. The progression of the tool wear is highly dependent on the volume fraction and average size of the reinforcements. Volume fraction and average particle size increases, the rate of flank wear is also observed to be increased. The increase in the volume fraction increase the number of hard particles coming to contact with the cutting tool. This results in a higher volume of tool mechanism, sorry, higher volume of material. This results in a higher volume of tool material being lost due to the abrasion of mechanism. From the, it is noted that the fine and well-distributed particles in the matrix reduce the tool wear and improves the machinability. It has been found that the coarser the particle, the more severe is the tool wear, and hence the better is the tool life. The cutting tool, when you cutting forces, when you measure against cutting speed, so it's a different kind of observation you can make it. So the main cutting force, feed force, thrust force, these forces are in the order it's given here. By cutting speed, generally contact is increased, rubbing is there, cutting force supposed to increase, but surprisingly here, the cutting forces are reduced. These experiments conducted depth of cut 1 mm, feed 0.1 revolution per minute, the volume fraction at 70%. If you see the wear of primary and secondary against the cutting speeds in meter per minute, so you can see the primary wear is high as compared to secondary wear. And again, you can also observe both of them are increasing at 250 meter per minute, and afterwards it is decreasing. So from those graphs, we can observe that the primary wear is maximum at the speed of 250 meter per minute, and the minimum at the cutting speed of 300 meter per minute. The secondary wear also maximum at 250 meter per minute, and it is least at the speed of 300 meter per minute. The cutting speed 250 meter per minute is critical speed at which the grow wear and nose wear rate is maximum. This is attributed to the failure of cutting edge as a result of softening of tool material with an increase of cutting temperature, and it is concluded that the critical speed is proportional to the hardness at room temperature. The hardness is proportional to the compressive strength, as you know. Hence, it is supposed that the compressive strength must play a significant role in increase of the critical speed, which shows the high speed cutting ability while machining of mathematics composites and cutting of relatively high thermal conductivity materials. The heat transfer from the cutting zone to the tool is resisted with the use of tool material with low thermal conductivity. The same for tool wear, we wanted to model, simulate, and find out the wear rate. So the final modeling which we have done for the same and using ANSYS LS Diana, we performed the analysis. The work is measured with the plane 162 element. Work consists of 4025 elements and tool 615 elements. The contact elements are used at the tool chip and work tool interface. Fine mesh is used at the tool tip. And formulation, Lagrangian, Eulerian, arbitrary Lagrange Eulerian, all the three are possible. Many researchers have attempted Lagrangian formulation, but it requires chip separation criteria based on shear failure, in which corresponding elements are deleted when shear stress crosses defined failure stress criteria. Accuracy depends on the size of the elements that are getting deleted. Even though fine elements give better accuracy, the computation time and cost is also accounted. Mesh distortion is another problem in Lagrangian formulation. When it comes to Eulerian formulation, it doesn't require any chip separation criteria, but the geometry of the chip should be known prior to the analysis. Hence, in this one, the chip geometry is obtained with the ALE formulation, and further analysis of wear is carried out by Eulerian formulation. You can have the models for the initial chip formation. So this is going to be ALE model. Tool is taken as the resid and moved. Output file with the geometry. Nodal results are written after chip formation. So then we have a contact between them. So when you delete and others, they have to grow. And if you see the second one, the chip growth, the output file of previous simulation is imported. The tool is fixed, and the left and right boundaries workpiece are defined as Eulerian models. The work is fixed in y direction along the bottom surface, and the material moves from left to right. The simulations continue till the steady state is reached, and the output file is written. Then again, we go for the steady state chip formation. The output file of previous simulation is imported. Tool is taken as a deformed material. Top of chip is constrained, and the Eulerian boundary condition is applied. The tool is fixed along X direction on the right-hand side face and Y direction on top face. These are the models corresponding to it. And typically, the governing equations used in our the constitutive relationships are those, and accordingly, the Johnson-Cook model is taken. The constants A, B, C, N, and M, the remaining are estimated from the analysis. And this is a wear rate which we can calculate with C and gamma are constants, and W dot is wear rate, Vs is the relative sliding velocity of the tool, and sigma F is the normal stress, theta F is absolute temperature. The sigma F, theta F, and Vs are obtained from the steady state chip formation analysis. Wear is calculated by multiplying with the time at each time increment. Then you can calculate those. These are the rate phases where the nodes identified, and the normal to that, when you couple to the previous, they are going to correspond to the measurement of the direction, the W, the direction which we can take from those nodes. The wear direction of each node is taken as the opposite to the resultant of the normal of connecting segments. Corresponding to the tool geometry is updated, moving the face nodes in wear direction, and the simulation is continued. And we can plot the flank wear width measured and estimated, and here also crater wear depth against the time. So we can calculate the rate of that, and we can showcase. After that, we have measured the surface finish, the quality of the components produced during the turning. Aluminum silicon carbide particulates, MMC, is important, as it influences the performance of the finished part to greater extent. Estimation of surface integrity can cater to the requirements of performance evaluation. Surface roughness is the final surface quality formed after machining. The surface quality of a specimen directly related to cutting speed, feed rate, and depth of cut. The aluminum silicon carbide particulate MMC material with aluminum 6061 as matrix with 10, 20, 30% silicon carbide particulate of size 10 to 30 micron dispersed uniformly. Right running tests at different cutting speeds, feed rate, depth of cuts were conducted in order to investigate the effect of various parameters on surface quality. Surface roughness of the specimens is evaluated with respect to volume fraction of silicon carbide particulates. The cutting tests were conducted using K10, K20, P10, P20, P30 carbide tools and the polycrystalline diamond tools to evaluate their performance. The surface roughness, this is going to be the late mission. The P-type tools and K-type tools showcased and the results obtained are the work materials were machined at 4 different cutting speeds ranging from 20 to 110 meter per minute with feed rates ranging from 0.05 mm per revolution to 0.4 mm per revolution. Each experimental trial was carried for 3 minutes duration. The average surface finish in the direction of the tool movement was measured in 3 different places of machining surface using a surface roughness tester. Finally, mean surface roughness in microns of the 3 locations were considered for each case. This is going to be surface roughness measured using surfatronic turning of 10, 20, 30%, as I mentioned. The surface roughness 20 meter per minute and at 100 meter per minute at different cutting speeds, and changing field rate you have, and the same at a different percentage of silicon carbide particulates. Surface roughness samples which have higher reinforcement ratio have higher which have lower reinforcement ratio. It may be due to fact that the tool is not cutting through silicon carbide particulate rather than peels off from the matrix. Higher the reinforcement, higher the number of pits formed, so higher will be the surface roughness value. We show that some of the silicon carbide particles are being pushed partially into the matrix while tool moves on the surface of the specimen instead of all being peeled out. It is also observed that the effect of peel on the surface is more predominant at higher reinforcement. And these are machining with K20 carbide tool. You can see here the work and the tool. The machining with P20 carbide tool, you can have the tool and work inserted. Again, tool you can see with K10. So 10%, 20%, 30% with the different cutting speeds and the feed rates, we can observe the surface roughness is decreasing while cutting speed is increased. And you can also observe that at 30%, it's going to be better. So we have calculated at the different feed rates and keeping feed rate constant, depth of constant, all the parameters have been studied. The depth of cut is increased to 1 mm, more will be surface roughness. It can be seen that the surface roughness ranging 0.8 microns to 0.5 microns using P30 grade carbide tool. At 0.15 mm per revolution using the same tool, the surface roughness ranging from 0.9 microns to 0.6 microns. K20 carbide grade tools, it is seen that the surface roughness ranging between 1.6 to 1.4 microns. So each tool we have conducted, even PCD you can have, when all the other parameters kept constant, including the feed while machining with the PCD as a tool with feed rate of 0.05 mm per revolution, depth of cut 0.5 mm, the surface roughness of the components was observed to be comparable to use those obtained from P30 grade carbide tool. The relative performance of the different tool materials with regard to the associated surface roughness may be attributed to differences in friction behavior between the tool and the workpiece materials. So 30% with 0.5 mm, and then here 0.05 mm feed rate, and feed rate is increased, and here cutting speed is increased. Okay, so depth of cut is increased. So to conclude, the maximum temperature is observed at the chip tool interface at a cutting speed of 50 meters per minute. That is 315 degrees centigrade. The temperature is gradually reducing along radial and tangential to the direction to the tool contact to the work. The temperature is also reduced from the chip tool interface to the tool flank and radial to the work. The experimental results are correlated with finite element results, and variation observed to be at steady state condition at 1.2%. It is observed that the most of the heat concentration is in the tool This phenomenon is entirely different in metals, where most of the heat is carried by the chip. The cutting temperature increase with cutting speed increase is less significant in feed and depth of cut. As the FA model is being validated, it can be used for the estimating temperature in metal cutting while machining MMCs with a different percentage of silicon carbide and aluminum particle weights. When cutting speed is increased, the nose wear will be the shape of the triangle and its wear rate increases. Higher the thermal conductivity and compressive strength or smaller the thermal expansion coefficient, higher the critical speed. The thermal conductivity is the most important among them as a factor to rise the critical speed. In cutting conditions of the critical speed, the groove wear on end of the cutting edge grows larger with the decrease of cutting speed. The groove wears in the shape of round or bands. The wear rate is measured at the cutting speed of 250 meters per minute and minimum at 300 meters per minute. Finally, the tool geometry is updated according to the calculated nodal displacement and one calculus cycle is finished. The program continues until tool reshape criteria are met. The user program continues until tool reshape criteria is reached. The number of calculation cycles carried out before user program stop is defined by dividing tool reshape criteria by the specified BN increment. The surface roughness decreases with increase of cutting speed, but increases with the feed and depth of cut. Among the feed and depth of cut, it is found that the feed is more severe than the depth of cut. The surface roughness value depends on volume fraction of silicon carbide particulates present in the matrix. It is found that surface roughness increases with increase of percentage of silicon carbide. Surface finish obtained with the P-type grade carbide tools better when compared with K-type carbide tools. It is recommended that for roughing cuts, K-type grade tools and for finishing P-type carbide tools can be adopted. Surface finish obtained with polycrystalline diamond tools is better when compared with carbide grade tools, but it is found that it has feed of 0.05 mm per revolution, a depth of cut of 0.5 mm. Same surface finish can be obtained with P30 tool as that of PCB tool. It can be seen that P30 carbide grade tools can be used at certain cutting conditions, which can replace costly PCB tools and hence reducing overall cost. Thank you. So any questions, queries, welcome you all.
Any questions from the participants? Please ask.
Yeah, good afternoon, sir. This is Madan Mohan here. Hello?
Yeah, please.
Sir, as you mentioned in the material non-linear, the viscoelastic material, you mentioned that a time-dependent material. All materials are, time-dependent.
No.
So how specially that you can explore that certain metals are only time-dependent, certain metals are not time-dependent?
Actually, the materials time dependent and all, it only while which process that you are considering. Whether you want time
actually,
dependent or not.
Sir, my point is viscoelastic material, once you said the time-dependent material, it means particular material only time-dependent and but not other time-dependent. All materials are time-dependent, I think so.
No, materials time dependence and all, not the criteria here. When you consider creep, it's going to be strain rate. Then the materials, the flow rate and all we required. Then time dependence is required. Same viscoelastic material, if we use for only elastoplastic condition, time dependence is not required.
Yeah, temperature dependent material we have to consider, no?
No, temperature dependent material, because that also depends again. Suppose your cutting conditions are at different levels where material changes its property, then we need to consider temperature dependent material properties.
Okay. So I think not certain metals are time dependent. All materials are time dependent, right?
Yeah, the time dependency and all, suppose what process we are doing. Material, fine. Material, you can take all time dependency. In the all materials can have time dependency. That is only
And,
a process dependency.
I got it. I understand very well. Sir, I would like to ask you one more question that how can you choose that this particular P30 carbide and K20 carbide are the suitable material where we can reduce the cost for the cutting tool instead of PCD tool?
Correct. The cost point of view.
Yeah.
I didn't get your question.
No, my question is that how can you get the idea that P30 carbide and K20 carbide are the suitable material that we can use for this particular project? Exactly.
No. Actually, if exactly means literature, the people have used for different silicon carbide particulates. So they have used even these tools. So based on that, and we tested here with the different tools and compared the otherwise.
It was a lot of work, sir, to analyze these particular tools among different, right?
Because this is the series of number of PhDs have integrated. Okay, so it's not one work.
Yeah, it's a very huge. That's what I'm asking.
Integrated are present to all. So we worked on the carbon composites. We worked on different kind of composite materials. All right. Okay. So there different tools are used. So when we go for the next research, the same tools and add some more tools. Like that, we have progressed with the different tools, and the same I have presented here. But each case need not use those the tools. And also second, availability.
Okay. And
because one advantage, all these materials available from Midani and in Hyderabad, the DRDL. So it's possible that they are also working on it. And sometimes they suggest that let us use these tools and give us some data. That is also another point here for working.
Okay. Thank you, sir. That was a great work, sir. Thank you.
Okay.
Any more questions from the participants? Okay, if no more questions, I would like to thank Dr. Ravinder Reddy sir for enlightening us with his presentation. It gave us good scope of research in the area of metal matrix composites. Sir, it was really beneficial for the researchers working on machinability of composite materials. On behalf of all the participants and organizing committee, I would like to thank you, sir, for information sessions. I would also like to thank the organizing committee for giving me this opportunity. Thank you very much, sir.
Thank you. Thank you all.
Right. Okay, the next session is going to start after the lunch break. Thank you all the participants.